You can do a struct or a class. It doesn't matter. If you do a class, just make it public. But otherwise, they're the same thing. And you all should know that. So, a linked list is a good application for pointers. I'm going to draw a little bit on the board here, kind of illustrate what this is. A linked list is a data structure. It's a way of structuring your data, kind of like an array, where you can link several different objects together. So, while an array, you have to know the size of the array when you make it. A linked list is dynamic. It can shrink and grow, and yet all of the objects are still chained together. Now, they are not necessarily right beside each other in memory, but they are still chained together, and so that's the advantage of a linked list over an array. It's dynamic in size. But anyways, we can create our objects. This could be any type of object. It could be a game object, it could be an employee, it could be anything created from a structure or a class. And we have lots of these objects in our program. And we want to be able to add a new object at any time, and we want to be able to add to the front of the list or the back of the list or anywhere. And we also want to be able to erase one of these guys at any time, and not break the chain. Everybody else is still chained together. Okay, so that's what we're looking to do. And this is called a linked list or a linked list. List. And like I said, these guys are all chained together. These are all nodes, by the way. So this is a node, and that's a node, and that's a node. They're all nodes, and each one has an arrow that points to the next. So that's the chain. Every linked list has a head. And a tail. All right, so if we add a node to the front, we'll chain it on to the rest of the chain, but then this is not the head anymore. That's the head. You get it? The head is always one end, the tail is the other. The last one, the tail, will have an arrow or a pointer that points to null. That's how you know it's the last one. So all of these guys have a pointer, which I have drawn as an arrow, that point to the next node, and then the last one has this thing that points at null. Tail points at null. All right, so does that give you some idea of what this looks like? In order for this to be true, what kind of pointer does this have to be? What's it pointing at? I'm not pointing at a structure or a class. You're pointing at an object. A what?
The next node.
A node. Yes. So what kind of pointer is it? This is a node, and I'm pointing to a node. What kind of pointer is that? A node pointer. A node pointer. So let's code that. Now within the structure of the node, I can create some data in here. You know, I could have some numbers, I could have some strings, I could have other stuff, whatever I need in my class or in my structure to make up this structure. It doesn't have to be called node, they just are nodes, so it could be called anything. But then can I put a node in here? IntelliSense says no. What happens if this actually tried to compile? Infinite loop. Yeah, it explodes. Because every time you create a node, you create another node, which creates another node, and so on, and yeah, it blows up. But can I create a node pointer? Can. In fact, we usually call it next. I can create a node pointer, and this pointer will point to the next node in the list. So in main, it kind of looks like this. We'll have node A and node B, and I can say A dot next equals B dot, not B dot next, just B. Except for, why does that not work?
Because there needs to be a point.
And if there's only two nodes in my chain here, then B dot next should equal what? Null, or if you want, null pointer. And then I need a node pointer called the head. And what does that equal? A, but it would have to be the address of A. Let's go ahead and fix this. These are not nodes anymore. These are node pointers. And so A equals new node, and B equals new node, and then I have to use an arrow instead of a dot. And then I don't pass the address of B, I just pass B, and the head is going to be equal to what? And then the tail if A's the head, who's the tail? B. And normally you'll want to iterate through this list. Now this can be just a way of storing all of this data, but you might want to, let's say, draw or update all of these guys or something like that. So when you're doing that, you usually have one more pointer on the outside. This one's called the current, the one you're working on, the current pointer. Guess where that starts?
At the head.
Starts at the head. and then it will kind of iterate along, do its thing, and ends at the tail, and once it reaches the tail, it's done, you put it back at the head, in most cases. So, you're going to have node current, and what would that be? The head. Or A. Either one, right? They're the same thing. So both pointing at the head, current and head are both pointing at A. A is also pointing at node A. So if I want to add another node here, how would I do that? Let's say I want to add C to the mix.
So you just said B arrow next equals C, where C is a new node.
Well, we don't have C, so we got to make C, right? And then what?
Yeah, you said B next equals
B next now equals C. And what else?
Now you need to set
C next needs to equal null. And one more thing. Tail equals C. All right, so that's kind of a manual update. You want, when you build a linked list, you want all this stuff to have functions that would do this for you. You want to be able to add a node. You want to be able to add it to the head or to the tail. And you want to be able to adjust it. Now, so we've got A, B, and C here. Let's add one to the head. How could we do that? We need to create a new node. So node Z equals what? Well, first we need to make it. Now what? Z is what? We could use A or head. Either way, it's going to the front of the list. So that will work. Head is better because head is going to always be right. But we could say A. What else though? What else happens now? Head equals Z. Is that it? Yeah, we're all linked up, I think. And so we've added one to the tail. We've added one to the head. Let's remove one. Let's remove B. B's getting nixed. How do we do that? You're going to delete B. All right, look at the board. Let's see what we just did. We got Z up here. We got A. We got B. We got C. C's the last one, right? Yeah. C's null. We're pointing at null, and this is our tail. And we just cut this guy out of the picture. So what's A pointing at?
C.
Nope. A is not pointing at C. It's pointing at the remains of a dead node. That memory could be used for something else now. What's pointing at C?
The dead remains.
Nope. Nothing. Well, the tail is, fortunately. fortunately. Otherwise, we'd have a memory leak. But if we had another node on here, we would have lost C. C would be gone. In fact, if we had had, 100 nodes on here, they would all be gone. Because when you break the chain, you lose everything to the right of it, except for whichever one this guy saves. So you have a memory leak. All right, with that in mind, let's rethink this. We want to remove B. What if we point A at C? What if we do that?
And then delete B.
We don't lose our chain, but what is the problem?
B should be still there, so we can
We don't have access to B.
No, we have B directly, but we don't have access to it through the chain. So now I could do this. I could say A equals A dot next equals C, and then delete B, and that keeps our chain intact and all. But if you don't have access to these nodes, like if I hadn't hard coded this, if I've just been adding nodes to a list like you normally would, this doesn't work either. We need to do this at some point though, right? We got to keep the chain intact. We can say current equals B. You might want a temp pointer to point at A. But if you say current equals B, then you can say, or let's just say current equals what? Current equals A. And then current next equals C. Or delete current dot next. That deletes B. We still don't have access to C this way. Temp is pointing at C. Does that work? All right, what is temp pointing at?
Next.
Pointing at C.
So this is A, this is B, this is C. So temp is pointing at C. And this works regardless of how long our list is or which node is pointing at. We have a temporary node pointing at 2 nodes over from current. Then we can delete the one in the middle, so that's B gone. And then we can fix the chain. We can say next is now equal to the temp. You follow? No? There are other ways of doing it. You don't have to use the temp. Now there is a site problem here. You need to check and make sure that this is not the tail. Because if you try to delete null, you're going to get an error. So you need an if statement that makes sure that doesn't happen. You also don't want to try to set next to something that doesn't exist. So be careful with that. You want to make sure that this is not null. But this is how you would kind of arbitrarily delete any node in the chain without losing any data. So that's one way of doing it. You get the idea of a linked list. What we want to do is create some functions in here. This might be a void. This might return a node pointer. I guess it could do either one, but you want a function that adds a node. And you probably want to pass it some data. All right, and here we also want some other node pointers in here. We want, I take that back. Take that back. Let's just create a whole new structure called a linked list. And here we want to have node pointers for the head, node pointer for the tail, node pointer for the current, and then you want your functions for add node, and then in here you're going to pass in whatever data you need. And then you want a function for remove node. And I think in the lab you're going to need 2 add functions. You need one to add to the head and one to add to the tail. So remove node will hunt down a node with certain data and delete it. You're going to have one that does it for the tail, and then you're going to have a display. And this is going to show all of the nodes, or display all of their information. So you start at the head and you show everything all the way down to the tail.